Okay, what we're going to look at today is a thing called Ionic Products, and actually it's the same thing as the solubility product. Same way to calculate it and everything. But it's where you're mixing two different solutions together rather than trying to dissolve a solid into water. Okay, so we're going to see if mixing 40 mils of lead nitrate and 10 mils of potassium iodide makes a precipitate. I'm actually going to do it experimentally first. So I'm not just going to put the same volume of each, because I want to make it a little bit more realistic to what you're going to get as an assessment question. Alright, so here I've got my potassium iodide. I'm just going to use 10 mils of that. So that's a bit too much. I'm not worried too much about precision today, to be honest with you, unlike what you're doing in physics at the moment. Okay, so I've got my 10 mils of potassium iodide, and I'm going to have 40 mils of lead nitrate. Now, nitrates are pretty much all very, very soluble, so we can say that that iron's going to have no effect on what's happening here. But just what I want to look at here is what's about to be reacted together, so we can see which species or which substance might be able to be a precipitate. So lead nitrate, you see I'm using equations to help do the chemistry, plus 2 moles of that. So for every mole of that, I'm going to react 2 moles of this to make lead iodide and 2 moles of potassium nitrate. Now I have not put states of matter there on purpose, because I don't know. I know these ones are aqueous, but I don't know what's going to be the case here. They might both be aqueous, or one of them might be in a dynamic equilibrium. Some of it will be in solution and some of it will be precipitated out. With my knowledge of potassium ions and nitrate ions, and the fact that there's this little rule that says that, or you used to learn that rule, is all potassium salts are soluble and all nitrate salts are soluble. That just means they're incredibly soluble. Okay? They've got very, very high solubility. They don't really have a Ks value. So I can be pretty sure that this is going to be aqueous. So the potassium ions and the nitrate ions from over here are going to be in solution. But I'm not quite so sure about lead iodide. Lead iodide does have a Ks value, and I looked that up just before and forgot it, so I'll check it again. But Ks of lead iodide is equal to, this will be given to you in an assessment by the way, 9.8 times 10 to the negative 9. Now you'll notice I've only got everything to 2 significant figures here, because that's about as precise as I can be with measuring cylinders. I can tell the difference between 10 mils and 11 mils. I can tell the difference probably a bit further than that too, but in this one here I'm only good for the nearest mil, so I can't be more than 2 significant figures here either. Alright, so that's why I've not gone 0.100, which these actually are. And I haven't got 9.8 whatever it is, or 9.79 or whatever it is. Excuse me, for this one. I'm just sticking to the precision I've got, which is only 2 significant figures. Now when I do mix them together, which I'm going to do in a beaker rather than a measuring cylinder, because it's a better way to do it, I see that, sure enough, I get a pretty cool precipitate. Okay? So I have made a precipitate. What that means is that the concentration of the lead and iodide ions in there is greater than what it would be for a saturated solution. Alright, because this is a suspension. But actually if I was to let it settle out, we'd observe no difference in this. And we'd have a dynamic equilibrium. We'd have lead iodide salt on the bottom, and above it, what sort of solution would we have? Saturated. Okay, so only the certain ratio of ions that will make a saturated solution will actually be present in solution. The rest of it is out of solution and is a solid. So what we need to do is to work out what our concentration of lead ions and what our concentration of iodide ions is from this here. Okay, and this might make a little bit of the stuff that we did last couple of lessons make more sense. So lead iodide's all we're looking at here. So the first thing I'm going to do is write its dissociation. Okay, its equilibrium that it's got. Alright, because that's where I've got to start. Okay, that's where I always start with these solution type questions. Then I had to work out what the concentration of each of these ions is, just using my NCV triangle. Okay, so remember, whoops, it's ugly, minus C equals N over V. And I've got concentration and I've got volume to find the number of moles in there. But actually when I put them together, it's no longer 40 mils and 10 mils, it's 50 mils. So I have to do a bit of calculating here. So, I'll get the calculator stuff on my computer so I can do that as well. Alright, so my number of moles of lead ions in here will be the number of lead ions in here that could precipitate or could form a solution. So, my first step here is that the number of moles of lead ions equals C times V. So 0.1 times 40 over 1,000. So I get 4.0 times 10 to the negative 3. When it goes into here though, it's no longer 40 mils, but it's 50 mils. So then I go, this number, and you still use the square brackets here because it's going to be used over here shortly. Okay, so that's N over the new volume. The new volume is 50. So, I should know this off the top of my head, but I'm going to use the calculator just to be sure. So, over 0.05, that's our 50 mils. So actually the concentration of lead is 0.080 moles per litre in this solution here. You might see now that actually I've done a very long-winded thing. All I needed to do is go 0.1 times 40 divided by 50 and I get the same number. Okay, it's very long-winded the way I did it. So let's just do the same idea for this. 0.1 times 10 over the new volume, which is 50. Okay, so it'll be a fifth of this. So we should hopefully know that's 0.02. So now I know the concentration of both ions. Excuse me. I can plug them into here. But before I do that, I need a Ks expression. Ks equals, now according to this, the concentration of lead ions that are in solution, or we had them in a solution to start with, so we'll use that 0.08, times the iodide concentration, but because it's got 2 in front of it, squared. Okay, so 0.080 times 0.020 squared. And so I will definitely use a calculator for this. I get 3.2 times 10 to the negative 5. Again, no unit required for Ks at this level of study. Alright? What do we notice about this number compared to this number? Okay? So actually, technically, this is not the Ks. It's actually the ionic product. Because that's the ions we did have. It's the product of the ions we've had. Hopefully that makes sense. Because IP, or ionic product, is greater than the Ks value, that's why we've got to precipitate. So what do you think the rule would be for if it didn't precipitate? Smaller. Smaller, okay? So you get a little rule being formed. If ionic product is greater than Ks, you've got to precipitate. If Ks is bigger than the ionic product, no precipitate. So they're all in solution. Spelling there. That's right. What do you reckon it's called if Ks equals the ionic product? So that's the other possibility. It's a special kind of solution. There's no precipitate seen. There's no equilibrium actually happening there. The harder one, isn't it? Spot on. It's exactly what it is. It's a saturated solution. Okay, so the actual saturated solution has got Ks equal to IP. So if I was to let this settle out and then use a dropper to just take the solution with no solid at all, then I'm taking out something that's got the ions in the concentration that they are, and then I'll work out the solubility of lead iodide in this here. So using that 4s cubed sort of thing for working out the solubility, which will give us those concentrations. This here can also be used for a thing called the common ion effect, which we'll do later, but we won't in video. Alright, because it's the same concept, where you've got an ion that's in your equilibrium system or in your solution being added. Will it form a precipitate or not? So you'll have a new concentration of one of the ions but not the other, apart from the dilution factor, of course. And that can be done in exactly the same way as we did there. You work out the new concentration of the ion that hasn't changed, and you now know the concentration of an ion being added. Right? So this here is predicting precipitation. So if you're looking for that in your book, that's the heading I think it's under. And these are the big things to remember. If you calculate using the concentration of the ions in the solution that you've made, solution, it's actually a suspension really, and you find that the ionic product is bigger than the Ks value, then you can predict that a precipitate will form. If, however, you find that the ionic product is smaller than the Ks value, then you would predict that no precipitate will form. And if they're the same, you say that no precipitate forms, but it is called a saturated solution. So that's the summary of all of that. The last thing I want to go through with you in the solubility thing is about a thing called the common ion effect, which was alluded to just before. Here I've got two saturated solutions of sodium chloride, alright? And so that means that I can't put any more sodium chloride in there. There's actually a heck of a lot in there. The common ion effect is basically saying that I can't even add one of those ions. I can't add any chloride, I can't add any more sodium. I'm going to show you what that actually looks like. I've got some ammonium chloride here, which is also a very, very soluble salt. And it will appear, when I put it in the left-hand one, to not do anything. It appears just to sit in the bottom. But actually it is doing something, we just can't see it. What's happening is it's actually starting to dissolve some of the ammonium ions. And in doing so, it is starting to turn some of the sodium chloride from the solution into sodium chloride crystals. So actually you've got a dynamic equilibrium formed in here now because I've added more chloride ions. And I can prove that. So I'm going to quickly check that I've got my universal indicator. By seeing if it's still neutral or not. And it's not, it's acidic. Well, actually sodium ions don't contribute to pH, so it can't be the sodium ions that change in there that's the problem. So actually what's happened is that there must be ammonium ions in there for it to be acidic. So actually some of that ammonium chloride has been dissolved. But in doing so, it's also precipitated out some of the sodium chloride. So that's one example where I've increased the concentration of chloride ions, which has shifted the equilibrium, as it were, for the sodium chloride backwards, making more NaCl solid. Right, and the one on the right-hand side, I've got the same thing, saturated solution of sodium chloride. In this one, I'm going to add a little bit of concentrated HCl. And hope that this works, because sometimes that's a bit touch and go. Because you're adding two solutions, hoping that HCl is concentrated enough. It's starting to go quite viscous, but that's just the acid. Obviously I need a bit more than that. When you're adding two solutions, it's hard to get the common ion effect to actually show you what I want it to. And it looks like that one's going to be a bit of a failure for us. Yeah, it is smoking a little bit, but that's more to do with the fact that I'm putting in concentrated acid into water, so it's starting to get a little bit hotter. Okay, sadly that one hasn't done what I was hoping it would, and I was really hoping that it would show that even when you add two solutions, if one's a much higher concentration, you will actually see some crystals form. But it seems that I haven't been able to achieve that with that one. That's alright, that sometimes happens with chemistry. You have a bit of an epic fail, and that was one of those cases. Okay. So after my frustration of not being able to get the salt to crystallise in there, I just poured bucket chemistry style some concentrated hydrochloric in there, and we can see now that there are indeed salt crystals in suspension in there that are slowly going to collect at the bottom. Further down, there we go. Awesome.